Hello, everyone. Welcome to this very exciting session today. We're going to cover geometric design. What you need to realize is that all the topics that we will cover today will be 20% of what you will see in the morning exam. And that's significant. What we cover is under the topic of, they call it transportation, but if you read it very carefully in the NCEES documents, under transportation for the morning exam, they only have geometric design. What we cover will be horizontal curves, vertical curves, horizontal curve offsets, vertical curve offset, sight distance, and within each one of these topics, I have several examples. And again, we will cover all the topics under the topic of geometric design, 20% of the morning exam. So please pay very, very close attention to today's presentation, because you will see problems similar to what we covered today on the exam, definitely. And those of you who will be taking the transportation exam in the afternoon, you will have these kinds of problems in the afternoon as well. Okay. Under the horizontal curve topic, let's begin with assuming that you are traveling on a straight road. Let's say we have you're traveling, let's assume, along a straight line like this, and then there is you want to travel and change direction to a different alignment. Now, what we need to do is provide a smooth transition between what we call the back tangent and the forward tangent. So the first alignment that you're traveling on will turn into in this case, a simple curve, which is also called a circular curve. And then you begin traveling on the second or the next alignment. Now, when we introduce the topic of horizontal curves, exactly it is that transition from the first alignment to the second alignment. There are certain terminology that we need to learn. And throughout this presentation, we're going to talk about these things. One is over here. Please take a look at the left-hand side of the screen, PC. Who can tell me what PC stands for? Okay. Point of curvature. Jeremy is saying point of curvature. Many of you are saying point of curvature. Absolutely. So point of curvature, here's what you need to recognize. That is the point where the back tangent, the first alignment stops and the curve begins. All right, so that's the point of curvature. Now, tell me this. That same point is also referred to as TC. Who can tell me what TC stands for? That's the same point. It's just a different name for it. TC, all right. It's called, guys, TC stands for tangent to curve. So that's tangent to curve. All right? And then there is a third way to represent that very same point. It's called BC. B as in boy, C as in Charlie. So BC. Who can tell me what BC would stand for? You're absolutely right. Ian says beginning of curve. Matthew also is saying beginning of curve. And the reason I say these three different terms, because interchangeably they do use on the test these three names. All right, so you need to recognize what they're talking about. Now, what about the point where the curve ends and the next alignment begins? Well, you see on the right-hand side, that's called PT. And that PT stands for point of tangency, point of tangency. All right, now two other things that I want to mention here, and then we're going to move on. This highlighted blue line, that is the distance we call back tangent, and then the next alignment, the next blue line that you see is the forward tangent. Let's go to the next slide, slide number 5. When you look at this slide number 5, there are various components of a horizontal curve that have been identified here. I'm going to walk you through the next few slides, and each slide will highlight one of these components, and we'll talk about each one. Let me tell you how these kinds of equations, these kinds of problems on the test work. Are you guys looking at this slide number 5? You see all these different components. What they will do is they give you 2 or possibly 3 of these different components represented by different nomenclature. And then they ask you to find the other variables. All right? So we need to understand what each of these letters represent. And if we are given maybe 2 or 3 of them, how do we find the rest? Well, in order to do that, we need to know the relationship between the various components. So next, we will look at equations that govern those relationships. All right. The very first component we're going to look at, this is, remember, for a simple horizontal curve. The first component is the radius. What you need to recognize is that a simple horizontal curve is a circular, which means it's part of a circle. It's part of a circle. And what do we know about a circle? Well, we know that each circle has a radius, and you see each one of those red lines that I've highlighted, that's the radius of this circle. And then, again, each circle has a center. So that center we call the center of curvature in this case. Now, the equation in the bottom of this page, and I'll place it in this box. This is a very important equation, so make a note of it, please. R is equal to 50 divided by sine of 1/2 d. Obviously, R is the radius. But this equation gives you the degree of curvature, which is d. in this equation. Take a look at this equation. But what I want you to highlight is this is the equation you use to relate the radius and d on the chord basis. On the chord basis. Put this in a box, chord basis. What it means, I will talk to you in just a few minutes. And also, you may ask, what is the degree of curvature? What is it and what does it represent? Please give me a couple of minutes. I will define that for you as well. Next slide gives you another equation. We call that the curve equation, but this is on the arc basis. Remember, the equation we looked at in the previous slide was on the chord basis. This is on the arc basis. So if you are expressing the relationship between the radius r and the degree of curvature on the arc basis, this is the equation that you must use. Now, the next slide, this one, I would not worry too much about the calculations that are shown in the bottom, but if anyone among you is wondering how we came up with that number, 5729.58, well, this equations on this page show you the calculations that comes up with that strange number. But if you're not curious about that, don't worry about it. This is not something on the test, but the equation will be. All right, now, on slide number 10, the equation that we are looking at gives us a relationship between, all right, now let me highlight this, between what I call the tangent. All right, so remember there's a back tangent and a forward tangent. Then we have in this equation r, which is, we already talked about it, it's radius. And then there is this third parameter, which is I. Now, you need to understand exactly what that I is. That's an angle. And that angle is referred to as the, let me change the color here. That angle is called the intersection angle. You see that here? That's very important because in most of the calculations, we need to know that angle. So it's the intersection angle, and please pay attention. The intersection angle is the angle between the extension of the back tangent and the forward tangent. The word extension is very important here, okay? So the angle between the extension of the back tangent and the forward tangent is defined as the intersection angle, and we use the letter I for it. Joseph is asking, what is the difference between arc and chord basis? As I mentioned before, I will define that. Just give me a couple of minutes. I'm sure that's the question that many of you are interested in, and we will define that in just a minute. And Meredith is asking the units for D and R. D is an angle. We'll talk about that. All the angles, by the way, that we talk about, all the angles are in degrees. Every angle that we will mention today, it is in degrees. All right, slide number 11 gives us the relationship between what we call the long chord. Now, please recognize that the long chord is always a straight line. Not necessarily horizontal, but it is a straight line, and it connects PC to PT. All right? The line that connects a PC to PT is called the long chord. All right? Now, this equation down here gives you the relationship between long chord, radius, and I. What's I again? You got it. The intersection angle. All right. Here on page 12, we are talking about the relationship between the following parameters. Look at the sketch. What I'm highlighting here is called, well, we refer to it as E, but please write down the words external distance. So E, capital E, stands for external distance, and it is the distance between the PI, which I will talk about in just a second, PI. So the distance between the PI and the center of the circle, midpoint of the circle. I said circle, this circular curve. Now let's get back to this term that I used, PI. Please write it down. PI stands for the point of intersection. Point of intersection, and that is where the two tangent lines intersect. Now, the three equations in the bottom of this page give us a relationship between the external distance, E, and T, which is the tangent distance. I don't think I mentioned that before, but please note, and this is very, very important, guys, the distance between the PC and the PI, we have defined that as the back tangent, but that distance we refer to as T, capital T, and that's in this equation down here. And of course, I repeat the first equation. E is equal to T times tangent of I over 4. Let's assume that they ask you to find the external tangent for a given curve. If you know the tangent distance, capital T, and if you know the intersection angle, I, then you can substitute it in here and find the external angle. I said the external angle, which I made a mistake. It's external distance. All right? Now, there are two other equations on this page, and these other two equations you can use depending on what the known values are. You can choose one of these other. Actually, you can choose any of these three equations based on what the known values are to find the external distance E. I have some example problems that will demonstrate this to us in a few slides. All right, continuing with these curve equations, the next one relates, look at the sketch here. What I'm highlighting in red, we refer to as that distance as M, capital M, and that is called middle ordinate. Middle ordinate, write it down. And that is the straight line that connects the midpoint of the curve to the midpoint of what we call long chord. Does everybody see that? All right. So if they ask you to calculate the middle ordinate for a curve, you either are given the radius, or you can somehow calculate the radius, somehow calculate the intersection angle, or that may be given to you. So make a substitution and come up with the value of M. All right? Now, this is the last equation we are looking at, and this is a very, very important equation because no matter what the problem is and what they ask you to do, more than likely you have to use this equation first before you use another one. All right? So pay very close attention to this. This gives you a relationship between L, and L represents the length of the curve length. All right, make a note of it. Just the letter L, capital L, is the length of the curve, and that is related to I, intersection angle, and D, degree of curvature, through this equation. So L is equal to 100 times I divided by D. Now, both I and D, those are angles, and they are in terms of degrees. Um, Paul is asking something, a question about the external distance. Yeah, what you're saying, Paul, is correct. E, the external distance, is the distance between the PI and the midpoint on the curve. All right. Let's take a look at page 15. Here, what I've done for you guys is to summarize the equations that we just reviewed. And I have had feedback from other folks like you who took this review exam, this review for the exam, and after they took the exam, one of the feedback one person made one year was that slide number 19 was most helpful on the test. Of course, every semester, every time we update and revise these presentations. So what she referred to as slide number 19 is now number 15. So basically what she was saying was the slide that summarized all the equations she found very, very helpful on the test. And I totally agree. What I need for you, all of you, to do, please, is to tag this page number 15, tag this, because for the rest of the presentation today, we're going to come back to it and review it. Not so much review it, but I would need for you to refer to it when we get to do actual problems, because today you're going to do a lot of problems along with me. All right? So the way it works, you look at the problem, you look at the values that are given to you, and then note what they're asking for you to find. And then you go through this menu of equations. I refer to this slide 15 as a menu of equations that are available to you, and you choose the one that contains the known values and the one that you're solving for. And I'll demonstrate exactly how that works. All right? And you can do the exact same thing on the day of the test. All right? Before we go forward, I want to point out a common mistake. A common mistake is thinking, and please make a note of it. This is a common mistake. People think that LC is the length of the curve. Well, it is not. Make a note that if you're calculating for the length of the curve, this is the equation that applies. L. L is the length of the curve. All right? This is a very common mistake. All right? So LC, what does LC stand for? Who can tell me? Long chord. Long chord. All right? So make sure that you don't make that mistake. The other thing, let me tell you about the units. Every angle that you see anywhere on this slide, they are in the units of degrees. All right? And something that I want you to pay attention to is your equation and your calculator. Many of the calculators that you use, they have a internal function where you can set that the angles are always either in degrees or in radians. Please make sure, and this is very important, please make sure if your calculator has that feature, when you're doing these kinds of problems on the test, make sure that it is set on degrees. I know one individual did not pay attention to this, and the exam, the internal function of his calculator was set on radians. So he treated all of these angles in radians, and what happens, the answer that you get seems reasonable, but it is wrong. It is in radians. So make sure that doesn't happen to you. All right? A couple of you are asking about the angle D. D stands for the degree of curvature, and as I said before, I will define it for you in just a second or two. All right? Also, Jeremiah is asking, what does E stand for? It stands for external distance. External distance. And Fahmy is saying, why are there two equations to calculate E? Actually, I gave you three equations to calculate E. Just the relationships work that way. There is no magic about it. All right, those of you, including Amber, that asked to what is the degree of curvature, or where is that angle? Here's your answer. All right, Amber? The degree of curvature on the chord basis. And someone else, I don't remember the name, someone else earlier asked, what is the difference between the chord basis and the arc basis? I'm answering that question now. All right? So two things. This slide is very important. It answers two things. First, what is the degree of curvature? And what's the difference between the chord basis and the arc basis? So please pay attention, because I know this is a question that many of you have. So first of all, degree of curvature on the chord basis is simply that it's defined as the central angle subtended by a chord of 100 feet. Think about that. Think about what I just said. The degree of curvature is defined as the central angle, meaning at the center of the circle. Remember I told you this is part of a circle, so it has a center. So at the center, that's called a central angle. So the central angle that subtends a chord that is 100 feet. Whatever that angle happens to be for a given curve, that is defined as the degree of curvature on the chord basis. At the very bottom of this equation, I have repeated the equation that gives the relationship between the radius and the degree of curvature in the terms of chord basis. Now let's move on. Slide number 17. this gives us the definition for the degree of curvature on the arc basis. All right, degree of curvature on the arc basis. Guys, this is the central angle subtended by an arc of 100 feet. All right, so the central angle, D, for a given curve that subtends an arc. Now, this is no longer a chord. It's an actual arc, part of the circle, all right, which is 100 feet. All right, so the angle that subtends an arc of 100 feet is defined as the degree of curvature for the curve. Matthew, uh, um, I'm not following what you're saying. Okay, here on page 18, it just gives you the relationship between the degree of curvature and the radius for a given curve. But what I'd like to do next is to start talking about actual problems. And here, I want all of you to please on this slide, we talk about an actual problem. So I want everybody to participate in this and solve this along with me. All right, Matthew, I think if you go through some of the example problems that we do, I think what you're asking will become clear to you. The 100 foot has nothing to do with the long chord. All right. The word chord that I used has nothing to do with the long chord. It's simply a chord on the curve that's happens to be 100 feet. All right. Let's look at this problem, and I need for everybody to participate. This and the other problems that I'm using in this presentation are very typical kinds of problems that you're going to see in the morning exam. All right. The bearings of two tangents connected by a horizontal circle are north north 50 degrees east. All right. Now, what does that mean? Does everybody remember the bearing of a line? Here we're talking about a line, a tangent line that has a bearing of north 50 degrees east. That's the back tangent. And the forward tangent has a bearing of south 35 degrees east. The tangent intersects at station 37 plus 00, and the curve has a radius of 800 feet. Guys, the concept of bearing is very, very important, and what I'm going to do is go through this problem, use this problem to demonstrate to you what bearing means. Certainly, you need to know what that means for a problem, for this problem, and then there have been questions dealing with bearings of lines just on their own, not necessarily related to a curve. So you need to know what that means and how to create it. But here we've combined the concept of bearing and horizontal circles. All right. So in this case, the curve radius is 800 feet. The curve radius is 800 feet. So also make a note of that. By the way, I have to tell you, in these horizontal curve problems, the surveyor, when she designs a circular curve, more than likely, usually the design parameter is either the radius or the degree of curvature, D. So the surveyor designs a curve based on what she decides the radius should be or the degree of curvature, and all these other parameters that we've talked about, they are calculated based on the assumed radius or the assumed degree of curvature. All right. Now let's get back to this problem. Guys, the concept of bearing, and I need for everybody to please pay attention. What does a guys? Did you hear that that command, that voice that came on? No. Okay, that's fine. That's fine. Then there's no problem. I did. Somebody said something to me, said a wrong command, and I guess that was just directed to me. So, all right. So we have the concept of bearing. This is what I need for you to do. What does a line that has a bearing of north 50 degrees east look like? I want you to go exactly through these steps that I'm going to outline next. All right? Look at the bottom left of the slide. The first thing that you do, you draw these directions, north, south, east, west. All right? Just identify that coordinate system. Then look at the bearing. In this case, it says north 50 degrees east. N stands for north. So here's what you do. Due north, you go exactly 50 degrees, in this case, towards east. Why towards east? Because it says north 50 degrees east. So the second letter tells you which direction to rotate. So there it is. So the bearing angle is 50 degrees, and it goes from north to east. And then once you do that, then create the line. Does everybody follow? All right? So this is basically the line with the bearing of north 50 degrees east. These bearing angles are always between 0 and 90. In other words, they will always be in the same quadrant. All right? Now, tell me something, guys. Let's see if you can help me create the second line. The second line, or the forward tangent, has a bearing of, look at top right, south 35 degrees east. So this is what we do. Let's go to the next slide. Now, create the coordinates here, north, south, east, west. At the end of the back tangent, which would be the beginning of the forward tangent. And then what do we do there? Well, take a look at the bearing angle, south 35 degrees east. Absolutely, you got it. You start from, the first letter is south. So south, you travel 35 degrees towards, in this case, east. So the second tangent has this orientation right here, as you can see. All right? That's all you need to know about bearings of different lines. Please learn this if you don't know how to do it. It's very easy, but something like this will be on the test, the concept of bearing. All right? Now, then we can use these different angles and come up with some relationships. What else do we know about this problem? This problem tells us, let's take a look at the known values. They say the tangents intersect at station 37 plus 0, 0. Now, the point where the tangents intersect, what did I tell you it's called? You're correct, PI, which stands for the point of intersection. Point of intersection. All right? What this says is that point of intersection has a station 37 plus 0, 0. The concept of station is very important. What that means is the location of the point from where the surveyor began his survey. All right? So there is a station that's called 0 plus 0. That's also called the point of beginning, POB, point of beginning, which is the station 0 plus 0. And then to keep track of different points along the survey line, we establish these stations. And in many, many cases, generally, we define the stations in 100-foot segments. So here we go. If we say the station of the PI is 37 plus 0, 0, that means there are 37 100-foot segments. So this point, PI, is 3,700 feet. In terms of feet, 3,700 feet from the point of beginning. All right? Then we have the curve is 800 feet. So here is the kind of problems that you will get. The information that was given to you, that's known, and then they ask you these different questions. So what is the length of the curve? So tell me, what do you do? Absolutely. You go to page 15. That's where I gave you a menu for the equations that are available. Do it now. Go to that page, page 15, please, and find the curve or the equation that gives you the length of the curve. Remember, I told you, make sure you don't make a mistake. L, you want the equation that has L, all right? That's the length of the curve. So make some substitution and tell me what you come up with for the length of the curve. Well, let me show you the equation. The equation is this here. I'm looking at slide 25. All right. So on slide 25, you take a look at it. The equation that you picked should be L is equal to 100I over D. All right. Now, I is the intersection angle, and what's D? D is the degree of curvature. Were we given those? Were we given the value of I or D? No. But we were given enough information to calculate those values. I'm going back to page 24, and please, I want everybody to pay attention. Since the radius was given, then I can use that relationship here to come up with the degree of curvature. I need the degree of curvature because it shows up in the equation for the length of the curve. All right? Now, if you do this correctly, D comes out to be 7.162 degrees. That's the degree of curvature. Now, a common question here is, how come I'm using the equation? How come I'm using the equation for the degree of curvature on the arc basis? Well, unless they specify to use the chord basis, always use the arc basis. All right? So we calculate the degree of curvature. And one other thing we need to know is the intersection angle. And the intersection angle here, you can simply calculated to be 95 degrees. Remember, the intersection angle is defined as the angle between the extension of the back tangent and the forward tangent. The way we calculated that, and please pay attention because this is a very popular question also. How did I calculate the 95 degrees to be the intersection angle? I'm using the bearing angles for this case. All right? So try to figure that out. Using the bearing angles, the angle of intersection becomes 95 degrees. Now, going back to slide 25, substitute in that equation, and you should come up with these. L is 1326.44. Many of you are giving me that value. So, and some of you are asking about metric units. Yes, as long as you're consistent using metric units, you could use that. All the angles should remain in terms of degrees, but instead of feet, for example, you could use meters, and everything will be cool. All right, now, what is the second question? What is the station of the PC? What is the station of the PC? Now, this is also a popular question, kind of a question on the test. All right, please pay attention. I want everybody to do this. This is really important. Given the information in this problem, can you find the station of the PC? Well, the station of the PC, remember what they gave us. They told us what the station of the PI is. So we need to know the station of the PC. Does everyone follow? This is how you do it. You take the station of the PI, which was given, in this case 37 plus 00, and you subtract, pay attention, you subtract the tangent, the length of the tangent from it in terms of stations, and what you end up with is the station of the PC. All right? And on page 25, we did exactly that. First, you have to calculate the tangent, and in the menu of equations, find the equation for the tangent, substitute the correct values. The tangent comes out to be 873.05 feet. And, that could be a question on itself, by itself. All right? So find the tangent, and what do we do from that? Subtract the tangent from the station of the PI. The station of the PI is 37 plus 00. And guys, pay very close attention to what I'm about to tell you right now. We're going to subtract the tangent in terms of stations. Now, what is the tangent? Tangent length is 873.05. 873.05. That is in terms of feet. So, in terms of stations, what do we have? Well, in terms of stations, that is going to be 8 100-foot complete stations. That gives you the 800. And then the balance is 73.05. So in terms of stations, we express that as 8 full 100-foot stations plus the change, which is 73.05. So when you subtract that from 37 plus 00, this is what you end up with. All right? PC has a station 28 plus 27. Guys, this is not very difficult, but those of you who don't do this on a daily basis, you may want to practice and understand how to subtract things in terms of stations. All right? And Stephen Marzi says, is the PI an imaginary station? Well, it's not so much imaginary, but it is not on the curve. The PI is not on the curve, but it is it's not on the curve, but it is we use it as a reference point. C.I.A is asking where does 47.5 come from? Shanna, 47.5 is I over 2. It's I over 2, and I showed you on the previous slide, the intersection angle is 95 degrees, so I over 2 is half of 95. All right, guys, the next slide is the next question is going to ask you what is the station of the PT? What is the station of the PT? This is a very, very high probability that this question will be on the test. All right? There's a good probability any one of these questions will be on the test. But this is very popular because I tell you why. Because there is a very common mistake that people make in calculating the station of the PT, and I will share with you what that common mistake is in just a minute. But what I want you to do, without looking at the screen, without looking at the solution, see if you can come up with the station of the PT. Remember what PT is. PT is the station where the forward tangent ends, where the forward tangent ends, or that's the point where the curve ends and we are on the next alignment. So how do you calculate the station of the PT? Do it on your own and tell me. Okay. Let's take a look at the solution. Hopefully some of you, at least some of you, have that. And Paul, what you're saying is not correct, and actually that is the common mistake that people make. All right. Ryan, I think that's yes. Yes. All right. Let's take a look, guys. I want everybody's attention here, please. Everyone, whatever you're doing, stop and just listen to me now. There's only one correct way to calculate the station of the PC. All right, and that is to calculate. I'm sorry, there's only one way to calculate the correct station of the PT. That's what we're looking for, PT. Make a note of that in big, big letters. The only correct way is to calculate the length of the curve, L, and add that length of the curve to the station of the PC. In this case, the station of the PC is 28 plus 27. We just calculated that together. All right? I repeat. The only correct way to calculate the station of the PT is to take the station of the PC and add to it the actual length of the curve. The actual length of the curve. Of course, we do that in terms of stations. So the station of the PT becomes 28 plus 27 plus 13 plus 26.44. And here it is. The station of the PT will become 41 plus 53.44. Now, let me tell you the common mistake. The common mistake is for people to take the tangent distance, capital T, and add that to the station of the PI. If you do that, that is incorrect, and I guarantee you the first distractor will be calculated that way because that's a very common mistake. So don't do it that way. All right? And please don't start arguing with me why it is so. Just accept it. If it really bothers you, send me an email later. But the only way, the correct way to calculate the station of the PT is to take the station of the PC and add to it the actual length of the curve, because the stationing will be done on the actual curve. All right. The next question is, what is the interior angle at the PI? There is an important point here as well. Also, don't make a mistake here, because they are asking for what's known as the interior angle. All right. Interior angle. Write a note to yourself. The interior angle is this angle here. This is the inside angle, the angle between the two tangents. All right? So in this case, would be 180 minus 95. All right? Next one. What is the tangent distance from the PI to the PC? Well, this we've already calculated. This we have already calculated, so this is just what we call T. We had to calculate this for a different part of this problem. What is the long chord? Now, this is where we calculate or use the equation LC, long chord. All right? And go through all of this to make sure that you get the same answer that I have. All right? Now, this one, it says, what is the external distance? Remember, external distance, we use the letter E. And Fahmy was asking, how come there are more than one equations to calculate E? Well, because those relationships have been developed, and really it's based on what is known. All right? If you look at these three equations, I actually listed all these three equations. We have three different equations to calculate the external distance. You can pick the one that you like to use, but really, which one you use is governed by what you already know. What is the given information? All right? So it doesn't matter which one of these you use. Just pick one. Now, to demonstrate that all three will give you the same answer, I did use all three, but you do not need to do that on the test. That would be like using the same bird by 3 stones, using 3 stones. Don't do that. But just pick one, and the answer would be 384 feet. Now, the next question, what is the degree of curvature on the arc basis? So use the equation that I gave you. On the arc basis, it comes out to be, degree of curvature comes out to be 7.16 degrees. Then the last question, it says, what is the degree of curvature on the chord basis? Well, to answer this, use the equation that gives us that relationship on the chord basis, and if you do it correctly, the degree of curvature comes out to be the same in this case, 7.16 again. Now, tell me, what does this mean? If the degree of curvature based on the chord basis is exactly the same as what you get using the arc basis, what does that tell you about the curve? Yeah, you got it. If the degree of curvature using the arc basis and the chord basis are the same number, that tells me no, it's not symmetry. What that means is the curve is very flat. Lisa got it right. If the degree of curvature is the same both on the chord basis and the arc basis, that means the chord of 100 feet is the same, very, very close to the arc of 100 feet, which means the curve is very, very flat. And of course, guys, if you carry out these digits to the right of the decimal point a few digits, there will be some differences that you will see, but that's what this means. All right, let's do example problem 2. This one, guys, this is very simple, but just a couple of exams ago, I used to not cover this, but a couple of exams ago, they had a question like this, and someone that gave me feedback, he says, I had a problem like that. I did not know how to handle it. Well, it's very simple. So I'll just spend a couple of seconds on it. But they can give you an angle in terms of degrees, 30, in this case, 39 degrees, 41 minutes, 54 seconds. And then they ask you to find that angle in terms of degrees. Um, the answer is down here, 39.69 degrees. But the way it works, please remember, there are 60 seconds in 1 minute and 60 minutes in 1 degree. So you start with the seconds, divide that by 60, 54 over 60 gives you how many fraction of a minute you have, and then now add that fraction to the 41 minute, which is 41.9 divided by 60. That gives you how many fraction of degrees you have. Added to 39, there's 39.69. Some of you have calculators that actually do this automatically for you, but they also could go the other way. In other words, they give you an angle 91.74 degrees. An angle is 91.74 degrees. Can you express it in terms of degrees, minutes, and seconds? The answer is given to you. This is very simple, but if you don't know it, you just don't know it. But it showed up on the test not too long ago. All right, we have another problem. I need for you to do this one. All right, I don't want to spend too much time on these problems because we also need to cover vertical curves and some other very, very interesting subjects today. And we have about an hour left, so let's use it wisely. Here, let's do this problem together. All right? The two tangents shown on the next slide intersect 2,000 feet beyond the station 10 plus 0, 0. The back tangent has a bearing of north 45 degrees west, and the forward tangent has a bearing of north 15 degrees east. The decision has been made to design a 3,000-foot radius horizontal curve. So that's what's given. You are asked to find the following items. What is the central angle of the curve? What is the central angle of the curve? I have not told you anything about the central angle. I did mention it at one point, and let's see who remembers what the central angle is. But let's take a look at the next slide, because here we have Donald actually gave me an answer, but we'll see if that's right or wrong. I'm sure it's correct, Donald, but we'll take a look at it. All right, this is the sketch, and at this point, some people ask me, or they have asked me in the past, will they give us this sketch, or do we need to create it? Well, more than likely, they will give you this sketch, but it is possible that they expect you to create it based on the description that they give you. All right? Now, here's the PI. They don't give you the station of the PI. However, they give you enough information that you can calculate the station of the PI. All right? And of course, they give you the bearings of both the back tangent and the forward tangent. And guys, here it is. Please make a note. this is the central angle. All right? The central angle. Now here, a lot of people get confused about the degree of curvature and the central angle. I'm going to explain it right now. So please pay attention so you don't ask me to repeat it. All right? The central angle for a horizontal curve is the angle at the center that subtends the entire curve. All right? I'll repeat it. It is at the center of the circle, the angle that subtends the entire curve, meaning it subtends the curve all the way from PC to PT. Now you tell me, how is that different from a degree of curvature? Well, please remember, the degree of curvature only subtends either 100 foot of the arc or 100 foot of the chord. In this case, the central angle subtends the entire curve. It could be several hundred feet. All right? So I hope that you realize the difference. However, I'm going to tell you another, I was going to say secret, but it's really not a secret, another point of information. And that point of information is the following. Write it down because this could be very valuable to you on the test. The central angle, as we just defined it, is equal to the intersection angle. So what we've been talking about all this long as the intersection angle, which is the angle between the extension of the back tangent and the forward tangent, geometrically, that is exactly the same value as the central angle. And it's because of the geometry of these two angles. All right? Joseph, what you say may have a typo in it. I will tell you, the central angle is the same as the angle of intersection. The angle of intersection. All right? Let me know if you accept and understand the difference. All right. Let's move on, guys. What is the central angle for this curve? Give me the answer. These are the choices. This is where the fun begins. All right? And I'm already getting some answers here. All right. All right. Some of you, well, those of you who are answering, you're saying either 60 or D, and you're correct. All right? So here it is. The central angle is 60 degrees, and really all you have to do is find the angle of intersection, and it's 60 degrees. There it is. Okay, let's move on to the next one. What is the tangent distance for this curve? What is the tangent distance for this curve? Go to page 15, find the appropriate equation, and see if you can give me an answer. What is the tangent distance for this curve? These are the choices. All right. Min On is giving me a choice. I won't tell you which one it is yet. Okay. All right. All right. So far, I have 5 or 6 answers, and you're telling me B is correct, 1732.05 feet. Okay. I accept that. All right. Guys, let's move on. What is the length of the curve? What is the length of the curve? Calculate it. Again, go to page 15, identify the correct equation, and don't make the mistake that I told you. Do not make that mistake. What's L? Come on, guys. For problem 3. Give me the number, not just the choice. A, B, C, D, E, if you can. Okay, I'm waiting for uh, Stephen. That's not one of the choices. All right. Okay, guys. I think. All right. All right. All right. I think. I think the number. Some of you, Stephen, actually came up with 3141.5. 3141. A lot of you are coming up with 3150. All right, 3141. I think I think this may be the answer B, 3141. But this is it's supposed to be 3150. Change this to 3150 if you could. Change that 9 to 50. And if you're coming up, yeah, Jeremy also is coming up with 3141. If your calculation shows 3141, that is correct. All right, and the answer would be something very close to that. All right, let's move on. What is the station of the PC? What's the station of the PC? They give you enough information that you can calculate the station of the PI. So if you know the station of the PI, how do you come up with the station of the PC? Always take the station of the PI, subtract the tangent from it in terms of stations. All right? And several of you, Stephen says 12 plus 67. Yeah. All right. So yes, this is choice E is correct. 12 plus 67.95. So those of you who are getting that's the station of the PC. All right. Next, what is the station of the PT? Remember what I told you about that. The station of the PT, there's only one correct way. So let's see what you get, and then we need to move on. Min on already give me the name an answer, and I believe it's correct. We'll wait for a couple of other choices. All right. Okay. 44.95. 44.95. This should be the station of the PT. Remember, the only correct way, take the station of the PC and add to it the length of the curve. All right? Make sure you do that correctly. Very good chance that will be on the test. All right? Now, let's do problem 6. What is the degree of curvature of this curve using the arc definition? Kendra has already given me an answer to this one. Jeremy is saying 1.9, so is Kendra. Guys, problem number 6, D is correct, 1.9 degrees. Make sure that you also get that. Let's move on. This is really important, guys, this next problem. This problem deals with, on the NCEES topics that they say will be on the test, this problem that we are about to look at, this deals with horizontal curve offset. Horizontal curve offset. Very popular kinds of question related to this on the test. All right, so let's learn it, and it's not that difficult. All right, the long chord LC of a circular curve is 600 feet. The intersection angle is 110 degrees. The one recommendation I have, when you start solving these problems, I'm not going to do it here, but on the page, write down, summarize what is given to you. For example, immediately write down LC is equal to 600 feet. I is equal to 110 degrees. Find the radius. So radius is one of the unknowns. Then, let's continue. The forward tangent of the curve needs to be moved this curve needs to be moved in 5 feet. All right? Pay very close attention to that. It says the forward tangent needs to be moved in 5 feet due to a right-of-way dispute. What radius curve would you specify to hold the BC at the same location as in the original curve? Guys, remember I told you BC in the very beginning of this very, very exciting presentation. I told you BC stands for the beginning of curve. It's the same point as we also call PC, all right? They use these things interchangeably, so be ready for it. Now, what radius curve would you specify to hold the BC at the same location as in the original curve? Let me tell you about these class of problems. If you understand one tiny thing about these kinds of problems, it'll make life a lot easier for you, and you'll be able to get these problems answered correctly. Remember, guys, the 5 feet they talk about? Now, I need everybody's attention now. When they talked about the 5 feet, please recognize that 5 feet is the perpendicular distance between these two lines. All right? When they say the tangent, the forward tangent was moved in 5 feet, that means it was moved in that direction 5 feet. So the 5 feet is this red distance here. A common mistake is that a lot of people just assume the 5 feet is this, let me see if I can show it, this blue line. It's not the blue line. The 5 feet they give you in these problems is that red line. All right? So if you recognize that, that will help you. Let's go to this page 41. All right? Page 41, basically, the area that I was talking about, I have drawn the free body diagram, if you want to call it, or I have enlarged that area. All right? So that's the 5 feet as I explained to you. What we need to calculate, what you need to calculate in all the problems like this is that distance we call x. All right? A common mistake, as I said, everybody thinks that x is the 5 feet, but it ain't. So the 5 feet is that line that I'm showing, the vertical distance between the two lines. But what you need to do is find the value of x. You need to know what that x is. So in this case, we can very easily calculate the x knowing that the intersection angle is 110. That was given. All right? That was given by the problem. So the intersection angle is 110. Then this other angle that I have labeled is 70 degrees. That's 180 minus 110. So if you know the 70 degrees, you know the 5 feet, the sine of 70 degrees would be equal to 5 over x. So calculate x. X comes out to be 5.32. Once you calculate that, then the new tangent Is everybody following this solution? This is very, very important, guys. All right? So the new tangent is simply 523.03 minus 5.32. All right? And that gives you the new tangent length after you have made the movement of the forward tangent. So the tangent length is now 517.71. And remember, the problem says, what's the new radius? So the new radius will be T new over tangent 55. And guys, where the 55 degrees come from? That's half of I. That's half of the 110. All right? So here's the answer. The new radius is 362.5. These kinds of problems, they all reduce to this little sketch up here, and I hope that you can follow it. I need to move to the next problem. This problem is very similar to the previous one, and I have included it for your learning enjoyment. So I'm not going to go through the solution here. It says um, the forward tangent is moved 120 feet forward. All right. So in this case, the tangent was moved forward. Again, remember, the distance 120 feet is that distance, perpendicular. And again, this problem reduces to this. I leave it up to you. Do it later. Find x, and then you can answer whatever they asked for. The radius and also t. The complete solution is provided, so you can follow it and make sure that you get the correct answer. All right? These last two problems, very important. Everything we've done so far is very, very relevant to the morning part of the exam. Now, the next topic that we're going to cover is vertical curves. Vertical curves also will be on the test, so we'll cover it. I need for you to understand vertical curves basically also relate to alignments, but these are in the vertical plane. And let's assume that we are going towards a hill, top of the hill. So we're moving to top of a hill, and what we need to do is somehow have a smooth transition to the next alignment. So in a vertical plane, we can think about it as a hill. That would be one way. That smooth transition would be like this. And let me tell you, here we have a parabola. All right, so write it down, please. Vertical curves are parabolic curves. All right, so it's a parabola. And here, the nomenclature that we need to remember, the point where the first alignment ends and the vertical curve begins, that we call PVC. PVC, point of vertical curvature. And the point where the vertical curve ends and the next alignment begins, we call that PVT. Then the straight line that connects the 2 points, PVC and PVT, that's called long chord. Now, one thing that you need to recognize is the point where the back tangent and the forward tangent connect. That we call PVI. PVI. And let me tell you something about this point. This is a point some this really is an imaginary point in the air, all right? We use it as a reference. Or if the curve is a sag, if it's below ground, it's a swell, for example, then the PVI would be somewhere inside the earth. But we use it as a, don't let that confuse you, all right? Because it's not that important. But that we use it as a reference, all right? Now, we don't have a whole lot of time to go through these things, so I'm going to explain it in a way that you could comprehend what you need to be able to do with vertical curves, all right? And I'll go step by step, and I will present to you the types of questions that normally show up on the test, all right? The whole purpose of a vertical curve is to recognize what the contour of the road or the natural elevation of the various points along the curve is, and in order to get the actual parabolic curve, we need to identify at each given station how much cut or how much fill we need to have, all right? Because at any given station along the vertical curve, the actual curve, to achieve its curvature, it has to have a certain elevation on the actual curve, all right? So the purpose of analyzing a vertical curve, really, and especially on the test, is to identify the elevation at a given point, at a given station along the curve, all right? So basically, that's what we're after. Let me explain to you a few other things. Properties of a parabola. These equations, don't get confused by these. Tag this page because we'll come back to it, and you can refer to it later. But I want to go back to, or go forward to slide 55. This is very important. I'm going to stay on this for maybe 1 minute, and then we'll do a problem together, all right? When it comes to vertical curves, I need for you to please learn how to use these three equations. This one, understand what E is. E is this quantity right here. Is the distance between the PVI, now this is for a vertical curve, the distance between the PVI and midpoint of the vertical curve. That we call E. Then this, I need for you to take a look at what we call L. L, guys, is the length of the curve. And the length of the curve, this is different from the horizontal curve. Now pay attention about what I'm about to say next, because a lot of people get confused about this. In the horizontal curve, L, length of the curve, is actually how far we travel on the actual curve. However, with vertical curves, the L, capital L, the length of the curve is defined as the projection of the vertical curve onto the horizontal axis. I'll repeat that. Projection of the curve onto the horizontal axis. All right? In this particular case, this is expressed as the length of the curve. Let me go to the next slide to explain this, and then I'll come back. For example, let's take this one. Let's take the curve. All of these are 4 different types of vertical curves, but the one left bottom, this one, the length of the curve is this. Let me also use a blue so you know. You see what I'm talking about, guys? The length of that curve is expressed as this blue line, which is the projection of the curve onto the horizontal axis. What about the one on the right-hand side bottom? Well, there it is. That blue line is the expressed or defined as the length of that curve. Does everybody follow what I'm saying here? One other thing is the gradient of these tangent lines. All right? So the back tangent, for example, here, has a gradient, or you can think of it as a slope. All right? So the back tangent has what they call G1. That's the slope of the back tangent. G2 is the slope or the gradient of the forward tangent. All right? G1 and G2, either one could be positive or negative. All right? Now let's go back to the previous slide. So now, the first equation here, top left, E, we know what E is. G1, G2, I just told you. L, I expressed what that is. And the denominator is just the number 8. All right, now, let's look at the next slide, the next equation. And by the way, that next equation is important because it does show up on the test. And what they're asking you to do is to find what's known as the rate of grade change. The rate of grade change. All you have to do, guys, is use that equation. All right, R is equal to G2 minus G1 over L. Let's go to the next slide here. All right, this is what they're going to give you. This could be all the information that they will give you about a vertical curve. So they will give you, let's take a look. First of all, at the very bottom, curve length, 800 feet in this case. All right, so the length of the curve in this case is 800 feet. Look for the gradient, G1, in this case plus 4%. So it has a positive slope. That means for every 100 foot of horizontal, this line goes up 4 units in the vertical direction. Now, what about G2? Gradient of the forward tangent is minus 3, so this has a negative slope. For every 100 foot of horizontal, drops 3 units. What else do we know? The station of the PVI is 65. All right, the station of the PVI is 65. And then Matthew is saying in slide 55, what does T mean, the capital T? I'm going to define that in just a minute. We will look at that together. Just a minute, please. Then they give you the elevation of PVI also. So think about what we have. We know the station of the PVI and the elevation at PVI. Let me tell you about the stationing of this. We are going to show the stationing on the horizontal axis. All right, so station 65 is here. The stationing is done on the horizontal plane. All right. So now pay attention. If the station at PVI is 65, please tell me. Any one of these questions I'm asking you could be some independent question on the test. What is the station at PVC? Think about it. If the station at PVI is 65, what is the station at PVC? Well, that is the function of how long the curve is. All right? So everything is symmetrical about this parabolic curve. Everything is. So Amanda is saying 61. Amanda is correct. And how do we do it? Well, if if the entire curve is 800 feet, well, C to PVC would be 400 feet, and C to PVT would be 400 feet. All right? So the answer is 61. Ryan, I don't know where you got that answer, but the answer should be 61. All right? Now, what is the station at PVT? The station at PVT should be 69 plus 00. 69, guys. 69. All right. Arash, everything is symmetrical. Don't worry about the gradient. All right? All right. Everything is symmetrical. All right. The next thing, guys, they can give you the information that I just gave to you, and pay very close attention. This could be a single question on the test. Could you please tell me the elevation on the grade line? All right. This is the grade line. All right. What is the elevation on the grade line at station 64 plus 00? Where is 64 plus 00? 64, station 64 is here. Does everybody follow? So what is the elevation on the grade line at that station? In other words, what's the elevation at this point? Who can tell me? Well, how do we do it? Use the slope or the gradient of the back tangent. That is 100 feet away from the PVI. So how many feet does it drop? 4. So what would be the elevation? Would be 260.2. First of all, I'm moving to 58, gives you the different stations. Now, look, guys, this is something that you should be able to do on the test. The elevation on the grade line at station 64 is 260.2. If they ask you, for example, what's the elevation at station 62, what would you do? Well, think about it. How far away is that from PVI in the horizontal direction? 300 feet. So if the line drops 4 in the vertical for every 100 foot, how much vertical drop will there be until we get to 62? Will be 12. All right? So that's how, all right, that you need to learn how to find the elevation at each of those stations. Does everybody follow? And the way, and you do it on the same way to the right of the PPI as well. All right? Same way. Now, the next thing you need to learn how to do is what I define to you as the offsets. All right? Now, I need for you to understand what we're talking about. What these elevations that we just looked at together, that gives you the elevation on the grade line. What we are really interested in is the elevation on the curve itself. All right? So, if we somehow, tell me if you agree, if we somehow could decide what this distance is between the tangent line at any given station and the elevation of the curve at that same point, if we somehow can calculate that offset, then we can find the elevation on the curve. And really, that is what we are after. All right? So let's move on to the next slide. Here. Slide 62 shows you exactly what I was just talking about. All right? It's called tangent offsets. And next, I'm going to teach you how to find that tangent offset for any given station. This is something that shows up on the test quite often. And what I will use, the equation that I will use to help you identify this is this equation right here. And somebody asked what that T was, and here we're going to talk about it. All right? This is the same equation that I showed you earlier. And you can use this equation to find the tangent offset. By the way, in that equation, this is a very simple equation. Let's find out what the ingredients are. In this equation, y, this thing, is the offset. So what we're calculating is the offset. Now, what are the other parameters here? Well, E, let's start with E. E is this distance here. And I gave you an equation that will give you that. So just calculate that, and that stays constant for the curve. All right? What about X? This X is important. X, guys, X is the distance between the PVC and the point on the curve that we are interested in terms of stations. Did everybody follow that? Lowercase x is the distance between the PVC and the point at which you're interested in the tangent offset value. But remember, that's in terms of stations. Then T, capital T, here is the answer to what you asked. The capital T in this equation simply is the distance between the PVC and the PVI in terms of stations. Think about it. T is always equal to half the length of the curve. Write it down. Big T is always equal to the half of the length of the curve. All right? Now, remember in this equation, X and T both are squared. Don't forget to square those values. Now, help me apply that equation to come up with the offset, tangent offset at station 64. Now, don't just follow don't look at my solution. Let's see if we can come up with the different ingredients. Y simply is what we're looking for, all right? What is X that you substitute? Remember, small x is this, the distance between the PVC and the station that you're interested in terms of stations. So that would be 3. Does everybody see why? Okay. Those are 3 stations. All right? So that's x, little x. What about E in that equation? E is 7, and 2 or 3 slides previous to this, I showed you exactly how to calculate that. I gave you an equation. So apply that equation, you should come up with 7. And what about big T in here? What did I tell you? T is always half the length of the curve. So T is 4. That's where this 4 comes from. E is 7. We got the 7. And then 3, I showed you where the 3 came from. Don't forget to square both 3 and 4. Solve for y, you come up with 3.94. Does everybody agree? Now, before we look at the next slide, I want you to give me the tangent offset at station 62, which would be approximately here. All right? So give me the tangent offset at station 62. Well, what would you use for x, small x? 1, because it's only 1 station away from 61. Does everybody see that? What do you use for E? 7. That doesn't change. What do you use for T? 4. That doesn't change. So what do you get for the tangent offset at station 62? Matthew says 1.75. Matthew changed his mind, says 2, and then Matthew changed his mind again, said 0.44. No, I think at station 62 is 1.75. Yeah. Does everybody follow that? At station, okay, at station 62, it's 0.44. Matthew says 0.44, and several of you are saying 0.44. Amjad says it's 1.75 at station 63. Guys, this is a very popular question, tangent offsets, and as you can see, it's not that difficult, so please learn it. Now, parabolic curves are symmetrical. So everything on the left-hand side would be a mirror image of the right-hand side, regardless of these g values. Gradients are different, but the tangent offsets on the right-hand side and the left-hand side would be the same, all right? Now, the next thing that you need to do, they will ask, for example, what is the station, at station 64, which would be here, what is the elevation on the curve? So what do? Pay attention. We take the elevation on the grade line, in this case, subtract the tangent offset, subtract the 3.94, and what do we get? Whatever we end up with would be the elevation on the curve at that station. And here it is. See these bottom lines? The values on the bottom line. These are elevation along the curve. And I hope that you understand how each one was obtained. Now, I have to tell you, they will not give you a comprehensive problem like this asking you to calculate all of these values. They will only ask you selected ones, all right? But that's the process. Let's move on. Okay, here is another concept. Brian, I don't understand your question. Here, this concept of the highest and lowest points on vertical curve. This is also something that you're responsible to be able to do. You know, these vertical curves have either a high point or low point. It's important for us to know for clearance or for drainage. Two things. Where are they located? And also, what is the elevation of the high point or the low point? So, what I'd like for you to do is these kinds of problems, I need for you to solve them using this equation. This is a very, very straightforward, simple equation. And x is equal to minus g1 over r. G1 is the gradient of the first tangent, back tangent. And remember, if G1 happens to be negative, this would be negative of a negative, all right? So make sure that you pay attention to that. And what is in the denominator, that's R, which is the rate of change of grade, rate of change of grade. I gave you an equation for it. In fact, guys, that equation is right here. All right? So if you're asked to find the low point or the high point, use this equation, calculate R. In this case, R comes out to be minus 7 over 8. Substitute R, and X comes out to be plus 4.57 in terms of stations. I need for you to pay attention and understand what this X is. This is not the elevation. This simply tells you how far away in terms of stations is the point that contains either the high or the lowest elevation. All right. So this equation just helps us locate that high point or low point. Todd is asking about the length L. The actual length, Todd, is in feet. For example, 800 feet. But in many of these equations, as I have explained, um, we are expressing that 800 feet in terms of stations. All right. Now this x comes out to be, in terms of stations, 4.57. So the actual station comes out to be 65 plus 57. All right, that is, pay attention to how we got that. It's 61, which is the station of the PVC. We added 4.57 stations to it, so we end up at 65 plus 57. That is the station of the highest point on that curve, this curve that we've been working on. All right, so the next thing, once we know the actual location of the high point, then we need to be able to find the elevation. Now, this equation down here, this is like Prego sauce. It's all in there. What I've done here, I have combined 3 different steps into one equation. If you don't follow exactly how that equation was calculated, please allow me to show you page 71. This is what I have broken it down into step by step. All right. Once you know exactly where the station of the high point is, this is what you need to do in order to find the elevation at that point. All right. Basically, I'll tell you. You identify the location, then you find the elevation on the grade or the gradient line, then you subtract the offset, calculate and subtract the offset from it, and it gives you the elevation on the curve. Follow that on your own, and if you have any questions, let me know. Problem number 8 is a typical vertical curve. I will leave this for you to review. Use this to practice what I just showed you. The next topic that we're going to cover is the sight distance. There are 2 more topics that are very important for the test that I will cover before we stop. This is the concept of sight distance, and then the next concept I'll cover today is vertical clearance, which is also a typical class of problems. We may go over time about 5 to 8 minutes today, if it's okay with you guys. Let's talk about the sight distance. Sight distance, minimum sight distance, is for safety on vertical curves, and there are different ways of calculating the minimum sight distance. But here I am using this one equation that I promote and I ask you to use. It's rather simple once you understand what the different parameters are. By the way, this S on the left-hand side, that is the minimum sight distance. That's what we're calculating. 8 is an 8. L is the length of the curve. H, guys, pay attention to what that is. H in that equation is the height of the driver's eye above the pavement. In other words, your line of sight, how far is it from the surface of the pavement? We usually use a number, 3.5 feet to 3.75 feet. Think about what that represents. With the SUVs that are so common these days, the higher value, 3.75 feet, is more likely. And in calculations, that's what we use. But you could go anywhere from 3.5 to 3.75. In fact, you can do this, whatever vehicle you drive, you can measure that for your case. When you're doing it, make sure nobody is around seeing you do that. But you can actually measure that. And then in the denominator, basically, G1 and G2 are the same thing we've been talking about before. Let's move on and see how we can apply this to this particular curve we've been talking about. By the way, L was given to be 800 feet. G1 plus 4%, G2 minus 3%, and H, as I indicated, told you what it is, and we're going to use 3.75 feet for that. You substitute everything in here, but I have to point out something very, very important to you. In this particular equation, the length of the curve is expressed in terms of stations. Please make a note of that. That's very important. So the length of the curve in this equation is expressed in terms of stations. So if it's 800 feet, you use 8 in here. You do the calculations. S, by the way, the equation gave you S squared. Well, we really don't need S squared. We need S. That's why we have a radical on the right-hand side of the equation. And then S comes out to be 5.8554 stations, and S in terms of feet is 585.54. So that's the number, but let's understand what this represents. This is the minimum sight distance for this vertical curve. So we calculate that, and then they may say, is this curve safe? Well, this is how you decide. If this S value that we just calculated, if this is smaller than the length of the curve, then that curve is indeed safe. Now, this S came out to be 585. The length of the curve is 800 feet, so we are fine. Now, what if you calculated this S and this value came out to be higher than the design length of the curve? Well, that vertical curve, if that's the case, then that vertical curve is not safe, and then what you need to do is to go back and increase the length of the curve to make it safe. Next, let's move on. Okay, this particular problem, this is the last concept that I want to share with you, and this deals with the concept of vertical clearance. Vertical clearance, which you're responsible for, all right? So let's see what we can do here. Read the words here, but what I need to point out to you is this. They say the proposed alignment must bridge over an existing railroad track, and this railroad track crosses the proposed alignment at station 28 plus 50. So far, so good. However, pay attention to the next line. The next sentence says the elevation of the railroad track at the point of intersection is 195. The proposed highway alignment must have a vertical elevation difference of 26 feet at station 28 plus 50 in order to satisfy vertical clearance requirement. This is your clue, guys. It says to satisfy vertical clearance requirements. And you can read the statement of the problem later with more care, but that problem reduces to this. Once again, these are common problems on the test. So here's what we're looking at. In order for this is the this is the issue here. In this particular case, you must have a clearance of 26 feet from here, which is the bed of the railroad track, to that curve at that point. All right? So you must have a clearance of 26 feet. Let's think about what we have, guys. What we know, Benjamin, what you say is correct, yes. The elevation down here is 195. Now, let's take a look at this step by step. The elevation at the railroad bed is 195. The clearance must be at least 26 feet. So, knowing that, what is the elevation of the curve? What elevation do we need the curve to have at that point? It's 221. That's the way we got that is 195 plus 26. All right? So that's 221. So it's a clearance problem. But please pay attention to what I will say next. This problem now basically reduces to forcing the curve, think about it, forcing the vertical curve to have a specific elevation at this point. Now, what is that specific elevation? It's 221 feet. All right? So this problem reduces to somehow forcing this vertical curve to have an elevation of 221 at the station 28 plus 50. All right, if you accept what I just said, then let me share with you an equation that I will present to you that will help you calculate what you need very easily. This equation, guys, can be used to force a curve to go through, a vertical curve to go through a fixed point, and that's exactly what we're doing here. This curve I found in a very old surveying book. I have misplaced that book, and I really don't know the reference for it, but it works simply and very easily for these kinds of problems. Let's take a look at it very carefully. L is what we're looking for. All right, that's the length of the curve we're designing for. Now, the ingredients A, capital A, I will tell you what that is. Offset, the word offset is used. That is nothing other than the tangent offset that we've talked about so far. And then the only other thing that shows up are G1 and G2, the gradients that we've talked about before. All right, now, what I need for you to do is understand what we are using for the value of offset. In this case, offset, we're using 2. I'm going to flip to the previous chart to tell you where we got the 2. The 2, guys, pay very close attention. That's the offset. This is it. All right? Make a note of it. That's simply the offset, tangent offset at the station that you're interested in. All right? So it's the difference between the elevation of the tangent line and the curve at that point. It's simply 223 minus 221. So that's where we got the 2. That's the offset. Now, what about A? Capital A. Now, a lot of people have difficulty with that, but that's simple. Write it down. A is simply the distance. I need to go the other way. A, now, pay attention. A is this distance between the station that you're interested in and the station of the PVI. All right? In this case, the station 28 plus 50 minus station 26 plus 0. So what do you get? 2.5 in terms of stations. Did everybody see how I got that? So A is the distance in terms of stations between the station you're interested in and the station of the PVI. And in this case, comes out to be 2.5. And then G1 minus G2 is 5. Make sure preserve the algebraic sign. All right? So substitute those values into that equation. The answer you get, the answer you get becomes uh, 10.91. All right? So we get 10.91. When you solve that, you get 10.91. So the correct answer here will be 1,000 feet. All right, so 1,000 feet is the answer. Now, a lot of people here, they ask me, they say, why didn't you go above the 10.91? In other words, you didn't choose 1,100. Why are you going to 1,000? Well, because that clearance, we need to know, I need to go the other way, because we need to have at least a minimum 26 feet. All right? The, the longer the length of the curve, the flatter the vertical curve becomes. So to ensure that we have at least 26 feet of clearance, we need to make it shorter. All right? Ryan says, did you just make up the offset? No, no, the offset is the distance between the elevation on the tangent line and this elevation on the curve. 223 minus 221 gives you 2. All right? Christopher says, where do you get the 223? The 223, it's either given to you or, look, you can get it from this information right up here. All right? You know the gradient of the forward tangent. You know the elevation at PVI. You can calculate that elevation of 223. Let me know if that answered your question. All right, you got it? Now, so there it is. The answer is 1,000. Then the next thing is, can you find the station of the high point and the elevation of the high point? I leave that up to you to do. We're running out of time. This problem 11, I did not plan to go over the solution of this, but this is also a clearance problem, but this is slightly more complicated than the previous one. So I would recommend just do this one if you're taking the transportation exam in the afternoon. All right, it's the same concept, but it requires trial and error solution. All right, but the complete solution is provided to you. These are the references that I've used for this particular presentation. I hope that you found this presentation helpful. And again, do as many problems of this kind as you can get hold of. And many people have given me feedback. This document that I have put together for you, this presentation, this is very helpful to you on the test, and many people have just used these problems and this handout to help them get through this part of the morning exam. I will be back with you about a week and a half, and my colleague will cover a very exciting two sessions next week. Have a great weekend. Don't forget, 10 hours a week of studies. So long.